we have Professor Bhunia. I think you can share your screen now, Professor Bhunia.
Yes, I'm ready to do that. So give me one moment. Let me know if you can see my screen.
Are you okay with Are you okay with us recording the session?
Yes. So I need to go over the slides. Yeah. So can you see my screen now?
Yes.
Okay. Wonderful. So go ahead.
Thank you so much. Again, it's my pleasure to welcome Professor Bhunia to be one of the keynotes for this colloquium. I met him as a previous conference, and he was kind enough to accept being part of this colloquium. I really appreciate your time. Professor Bhunia is a renowned scholar. He's a professor of cybersecurity and Endowed Chair of Internet of Things at the University of Florida. He serves as the director of Warren and Nelms Institute for the Connected World. Earlier, he was appointed as a TNA Schroeder Associate Professor of Electrical Engineering and Computer Science at Case Western Reserve University. He has over 20 years of research and development experience with 10 authored, edited books and over 350 publications in peer-reviewed journals and peer conferences, and 40 granted patents. His research interests includes hardware security and trust, adaptive nanocomputing, and novel trust methodologies. Dr. Bhunia received the IBM Faculty Award, National Science Foundation Career Development Award, Semiconductor Research Corporation Inventor Recognition Award, IEEE Host Hall of Fame Award, University of Florida Research Foundation Professorship Award, and many awards actually, and has several Best Award nominations. Awards and nominations. He's a co-founding editor-in-chief of the Springer Journal on Hardware and System Security. Dr. Bhunia received his PhD from Purdue University on energy efficient and robust electronics, and he's a fellow of IEEE. He will be talking to us about a very important topic related to this colloquium, which is about microelectronics assurance and untrusted supply chain, and where can AI help. Please welcome Professor Bhunia, and floor is yours.
Hey, thank you, Musha. Really great pleasure to be here in this IC2Tech annual colloquium forum. This is looks like an excellent forum. You have got a good set of outstanding panelists. I was listening to the panel earlier, and I also, of course, my co-keynote presenter, Walid Khalil. Great to be in this platform. My pleasure to talk about this very important topic. As you, Musha, correctly mentioned, microelectronics assurance is a pillar in cybersecurity, and I think it's not adequately researched, adequately taught, and I will hopefully be able to raise some awareness and share some really cool cutting edge research which my group is doing in this area. And most importantly, I would like to highlight the problems in this area so that the budding researchers, I know there are some students here, can take this problem and do some interesting research in this area and then go to industry or federal agencies and practice in those areas. So again, my pleasure. It was actually nice to meet Moshe in the SATC conference in Dayton recently. It was a great pleasure. And hopefully we can start doing more work together in research, education, and outreach areas. So this is briefly the content of the talk. First, I will talk about where the future of computing is leading us. Okay, and I think all of you are familiar, but I would like to set the ground there. I will talk about what's the future of computing at system level. Also at a device/integration level, I will briefly talk about what the future lies in front of us. Then I'll talk about why hardware security is important. Now, I think cybersecurity, all of you are aware about, but when you talk about the broad cybersecurity of systems and networks, how important is hardware security in that perspective? Then we'll talk about what is the future of hardware security, some of the very important problems in the domain of hardware security, which I have been working on for last 17 years or so as a professor. And then finally, I'll talk about how generative AI can play a role in hardware security, in particular system level security. So that's what my talk would be. And again, feel free to stop me anytime. I would like it to be interactive. Of course, you can keep your questions till the end. And that's okay also. But I'll be fine to stop in between and answer your questions. So this is the institute where I belong at University of Florida. This is Colloquium Nelms Institute. This is basically the Internet of Things or IoT Institute at University of Florida, funded through generous donation of two of our alumnus, David Nelms and Semmoto. They donated money towards establishing this institute about 7 years ago. We have a strong leadership team, as you can see on the top left. I'm really proud to have them, and we have about 50 faculty members, 100 graduate students. I call them the IoT army, and together they are developing very enabling IoT technology and their applications in many different fields for solving really practical global problems in those fields. We are actively looking for collaborators, partners, sponsors from industry, academia, and government. If you are interested to work with us, we'll be happy to have you as a partner. We are pretty open to create collaborations. We have created a lot of collaborations with many different universities, so we'll be happy to work with you um, in any role. If you're leading a proposal, you want us to help with that, we can do that. We can bring you in our proposals. We can also do a lot of curriculum developments together, outreach activities together. So you let us know how you would like to collaborate with us, and we'll be happy to go by your terms. Now, let's talk about what's the future of computing, right? I think, as I said, you know about that. A very interesting development that's happening for last several years is in the field of Internet of Things, or IoT, or also called edge computing. Now, edge computing is basically coming into existence from the good old embedded systems, which are, as you know, very specific computers optimized for target applications with very tight hardware software integration, right? So there are a lot of different embedded systems you have probably seen, digital cameras, DVD players, personal assistants, CPS receivers, and gaming systems, a whole bunch of embedded systems we have seen over the last 40, 50 years, right? Now, when you combine these embedded systems with a generous amount of connectivity where the devices can connect with each other as well as with the internet, and then on top of that, you add smartness in the form of machine learning or AI algorithms running on the data they are collecting through the onboard sensors. And finally, when you add security and interoperability to them, you get IoT, right? So that's the recipe which I use to talk about IoT, because when somebody asks me what is IoT, so this is my definition of IoT, or edge computing devices. But one interesting thing that's happening for the last few years is that typical IoT devices or edge devices would rely on cloud intelligence, which means that the data would go to the cloud would run complex AI or machine learning algorithms for recognizing patterns, for making decisions on the data, and then it will send back the decision to the edge or IoT device. So that was happening for last several years, but gradually that trend is shifting to something called edge intelligence, where the intelligent processing is happening at the data source, at the edge or endpoint devices, like an automotive system, like your smart speaker, like your smart thermostat. So if you think about these endpoint computing devices which are loaded with a whole bunch of sensors, they're interacting with the physical world, collecting the data. Those devices are now having a lot of AI ML algorithms running on them. So they are becoming quote unquote intelligent and smart. And that trend is is the most important trend right now, which means that we are moving from cloud intelligence to edge intelligence. And there's an interesting name for that. It's called AIoT, or artificial intelligence of things. So we are moving from IoT to AIoT. Now, of course, the moment you have a big shift like that, it gives you a lot of opportunities. It also brings you a lot of challenges. And of course, one of the important challenges is in terms of security and privacy. And we'll talk about that as we move along. Before we go there, if we talk about security, I would like to talk about some of the really cool edge devices or IoT devices we are developing in our research lab. And if you happen to visit Gainesville area, which is about 2 hours drive from Orlando, 2 hours drive from Tampa, 1.5 hour drive from Jacksonville, 4 hours drive from Miami and Atlanta. So if you are nearby, please feel free to visit us. We will be happy to host you and show you the lab we have. This IoT lab has a whole bunch of very interesting edge devices. Now, one class of devices which we are very proud of, which we are building for last couple of years, is called pastables. I think you have heard about wearables like your smartwatch, smart ring, like that, which you can wear. However, pastables are the devices which are stick and pill embedded devices or IoT devices, which you can attach on any surface, including on your body. These are like smart band-aids. You can put on your body. It can monitor different physiological parameters, different environmental parameters, parameters about your movement, and all those things. And by doing that and running some intelligent AI ML algorithms on the device itself, it can do a lot of interesting things. And it's led to a huge number of collaborations between our lab and the Department of Orthopedic Surgery and few other medical departments at UF. UF has a very big medical school. And we are proud to collaborate with a number of doctors who are saying that, okay, if you can monitor a patient before surgery, after surgery, if you can monitor this parameter versus that parameter using on-body stick and peel banded-like sensors, then that can be truly enabling. And that's what led us to the development of this new breed of IoT, smart IoT devices or edge devices, which we call pastables, because you can paste it on any surface, including in your computer, including on your computer, like a post-it or on the wall. Anyway, so this is again leading to a number of collaborations. On the top right, you see a collaborator, Dr. James Tushan, who is actually lead of the ankle and foot surgery department here in the orthopedic surgery department, and then a sub department actually. So he's head of that foot and ankle surgery sub department under orthopedic surgery, and we are working with him to develop a very smart stick and pill sensor for the feet, which can measure the pressure pattern and then tell a patient whether the pressure pattern is right before and after surgery. So anyway, there are a lot of examples of that. Again, if you are visiting our lab, we'll be able to show you. The reason I'm giving you this example is that security and privacy is extremely important for those devices. The other device which we are building for last several years through a grant from National Science Foundation is a device called spectroscopy at edge. And in this device, you can basically add something effectively to your cell phone. This device is not in that form factor yet. Right now, we have kind of a very portable scanner. You can see on the bottom right, which can be used to scan a specific material. Now, it can be a bottle of medicine. So, there are 10% of medicines in the world are fake or counterfeit. And these fake drugs, and as well as supplements, which can have unacceptable, harmful chemicals. And there are numerous examples of that. Also, harmful food additives. You need to detect them before you consume, and this device can do that. It can also detect illegal substances like fentanyl very effectively in the field. And the portable form factor with the added AI ML based intelligence, which can detect a particular material or substance very reliably by comparing the signature, spectroscopic signature with the signature stored in the cloud. It can be extremely helpful for law enforcement, for even consumers to detect any harmful chemicals on in a substance. So this is a device which led to numerous publications and cover stories, as well as a student actually opened a company to commercialize this product called Resonance Signatures Incorporated, and they also received an NSF-SBIR fund to commercialize this product. So the reason I talked about these few examples, there are of course a lot of them in our lab, but the reason we did that is that these are the examples where IoT is impacting our lives and industry in many, many ways, in many different fields, from transportation to energy to education to healthcare. And because of that, there is a huge growth rate of these devices. The IoT market is predicted to have 1.8 trillion USD by 2028, and this is by the statistics from statista.com, with a compound annual growth rate of about 25%, which is a huge growth rate, as you know, compared to any industry out there. And then the number of devices right now is 18 billion, and this is expected to be 40 billion by 2020, 2033. So it's extremely high growth rate, and these devices are going to be everywhere. So my students ask me that, Professor, everyone is talking about AI, should be everywhere, right? And in everything, and improving our life in every possible way. But what would be the carrier of AI everywhere? If you think about remote fields, where let's say maybe a farmer is using a machine to farm something in that, and then maybe a small industry in a remote village. So how the AI will go there? How AI will touch every aspects of our life? The only way to do that would be to use these smart, tiny, sensor-enabled computing devices or edge devices. And if you can run AI in those devices, then AI can touch every corner of our life, right? So and then that's happening, and that's why exactly you will see this huge growth, this compound growth of 25%, leading to about 40 billion connected devices in 2033. However, these devices require security and privacy on them, because you need to protect our data, we need to protect our lives. On interesting statistics, I wanted to also present to you. Again, this is borrowed from Statista. And in this case, you can see that the number of millions of households which are having smart devices, from smart speaker to smart smoke detector, that is growing significantly. You can see in 2022, we had, for example, just in terms of smart speaker, we had 131 million devices, and then it's going to be about 335 million devices by 2027. So it's a huge growth rate only in that market. But if you think about other markets, of course, the total number of devices, smart connected edge devices, that is growing at a very significant rate. I was going to say exponential. It's not truly exponential, but it's definitely a huge growth rate, as you can see in terms of the number of devices in the field. Now, when you build these devices, when you build the system, then you have to think about the major design parameters. So typically, the design parameters for embedded systems have been area, power, and speed, and we all know that. However, gradually security is becoming so important that it's actually becoming a first-class design metric. So we have to consider security at design time, at verification time, also at system validation time. And that's why right now we're moving from pass metric to pass metric, PASS metric, which includes security, right? Now, of course, if you think about these devices, many of these devices are interacting with the actual physical world. If you think about a smart autonomous vehicle, it's actually interfacing with the physical world. If you think about a smart toaster, you think about a smart um, thermostat, all of these devices are interacting with the physical world, and which basically means the safety of the user, safety of the physical assets also is in important, interesting interplay with the other parameters, including power, performance, and security. So that's why safety has to be an important parameter. Now, gradually, if you think about the number of parameters we need to consider during the system design, that would grow over time as security, safety, trust, smartness, reliability, all are becoming so important. Now it's a multi-objective system optimization. That's why the IoT and edge design space is evolving, and the design itself is becoming more and more complex, where you need to account for all these parameters at the same time. Right? No, so that's why it's an interesting challenge. We will focus on the security aspect, but I would like you to keep in mind that security is not the only parameter. If you have to incorporate security, you have to make sure that the other parameters are also considered, depending on the priority, depending on the target application. You probably have to give higher priority to one parameter to the other. One can be objective for system optimization, other can be constrained. Now, depending on your target system, these things might change. But in general, security would remain as an important parameter to consider. Now, you might ask, the embedded systems are there for last 40 years or so, right? Maybe even 50 years. And why the security of embedded system is different from the security of IoT or vice versa? What is new about IoT or edge security? Now, no, they are really not exactly the same. There are a lot of important new challenges in the IoT and edge security domain. And let me quickly talk about the major challenges here. The first one, as I mentioned, is that they interface with the physical world. More and more of these devices are interfacing with the physical world, particularly if you think about autonomous vehicle. Now, security has an important and interesting interplay with safety, and that's something you have to consider when you deal with security issues in autonomous vehicle. Many of the devices would have long, complex life cycle during which the security requirements would evolve, new standards of security or new attacks would surface. And because of that, it's important that your security is configurable or at least updatable. Software security has seen a significant benefit due to the aspect of patchability. If there is a security flaw, most often you can patch, and that flaw would go away. For hardware, unfortunately, hardware is typically not patchable, even though we have done some work to develop patchable hardware. But this, at least hardware, firmware, software, when you think about the combined integrated system, at that level, you need to make sure that the security can be upgraded during the complex lifetime. Typical devices, for example, in military would last for 10 to 20 or even sometimes 30 years. Now, that's a long time for an electronic device. And during that time, you should be able to update the security for the device based on to adapt to new attacks and new requirements. Then many devices are mass produced in the same configuration. For example, if you have a smart light bulb, the configuration for both hardware and software would be identical, and that means that you need to make sure that attacker would not be able to gain knowledge by reverse engineering one device, then use the knowledge to make a meaningful attack, to mount a meaningful attack on another device in the field. Many devices are never intended to be connected to the internet. And because of that, they do not run complex internet security protocols. They are not even equipped to do that. Many of them are run on bare bone processor. They do not have a full-blown operating system running. And sometimes the operating system will be very limited. For example, if you think about a smart light bulb, it may not run a full-blown operating system. So how do you incorporate complex cryptographic protocol on those devices if there is no OS? This is a very, very important challenge, and we have to still do enough that you can maintain the security and data privacy. And if you have a weak link, unfortunately, in the network, that might create a loophole for the entire network of connected devices, right? And that can be the weak point where the attacker can have an entry to the network and compromise the whole network. And that has happened. Probably you have heard about the Dyn cyber attack that happened a few years ago, where an adversary could use about 1 million interconnected IoT devices to launch a distributed denial of service attack. Now, many of these IoT devices are doing machine-to-machine communication. A machine is talking to a machine. There is typically no human in the loop, and anytime you have a machine-to-machine communication, authentication becomes a problem. A machine can potentially compromise another machine, and we have seen that a lot. So that's a big problem. And then that's happening most importantly because these things are connected, heavily connected with multiple devices, and then finally to the interconnect. So there are a lot of ways one machine can compromise another machine. Physical attacks are becoming more dominant for IoT devices because they are deployed in many times in a field where the adversary can gain physical access to the device. And if the adversary can have physical access to the hardware, then there are many ways it can lead to information leakage, it can lead to tampering, it can lead to other types of compromise. And this has happened for military drones. If you search Google, you might see that military drones have been captured by enemies, and they have been able to successfully reverse engineer, clone, bypass communication, or tamper the device. And then the last 2 points are also very important, that you need to incorporate security. So that part I think we all agree on right now. But security economics is very, very important. Typically, nobody wants to pay for security. And then how do you make sure they incorporate enough security measures at an acceptable cost, or ideally at zero cost, right? So that cost barrier is actually a big barrier for incorporating security solutions in a device. And finally, as I mentioned, IoT is not just one device. IoT is basically a whole network of connected devices which are talking to the internet, and maybe another set of connected devices are connected to the internet at the same time. So there has to be a holistic view of security, not just one device security to bring security to IoT. And that holistic view would require significant rethinking of IoT security. So that's about the computing paradigm. We are moving from cloud intelligence to distributed edge intelligence, as I mentioned, okay, through the distributed edge computing devices. But on the other hand, at the hardware level, if you think about microchip level, there is another revolution happening at the same time. And this revolution is called advanced packaging and heterogeneous integration. Particularly for chiplet-based heterogeneous integration, it has become very common these days, very promising, where you can have tiny chiplets optimized for specific functionality coming from ideally different third-party vendors. They are integrated, these diverse heterogeneous chiplets are integrated in a single chip, in a single 2.5D or 3D chips using a common interposer technology. And this technology is so powerful and economically viable that most semiconductor companies are looking at this technology. Some of them have already applied these technologies in their chips. However, they bring in some interesting security implications. Of course, you have to think about these new attack surfaces. The moment you have untrusted chiplets integrated into one 3D IC, coming up with a secure, trustworthy 3D integrated circuit using untrusted, potentially insecure chiplets is a very, very interesting research problem. As I mentioned, there are some new attack vectors that can come into play because of the integration of chiplets, particularly when the chiplets are communicating with another chiplet or among them. So that inter-chiplet communication is a significant problem, and anybody, or it's possible for an attacker to snoop into that, to create malicious modifications to alter the communication, or to corrupt the communications, or to provide unacceptable access control to the chiplets. So there are many different new attack vectors people have looked at, including my group, which are feasible for a chiplet-based 3D system. So to avoid these security problems, one can come up with a design solution, so security-aware design, where one can basically have, for example, a trustworthy chiplet, which can incorporate the trust and security for the other chiplets. So it can effectively act as a trusted enforcement engine and security monitor for the other constituent chiplets in a design. So that's the design part. There will be other solutions. There can be other solutions also. If you think about the current industrial practice, they address this problem by heavily encrypting each and every communication across chiplets, and that comes at a huge cost, and they do not want to do that. So there has to be a better solution for the industry to adopt so that they can avoid indiscriminate heavy encryption of the traffic between the chiplets. Now, one can also do analysis of security so that at the design time we know what are the security problems there and how we can address them. And finally, we need to verify for security at different stages. Once the chip is manufactured, we also need to do a test and validation for security. So that's definitely an evolving area in terms of the device or hardware where we need to pay attention in terms of incorporating security solutions. Now, when you talk about hardware, I would like you to know that there are three different areas of technologies. One is called ASIC, that stands for Application Specific Integrated Circuit. And these are full custom design. If you want to create a microchip, you create your own design, you tape out and you send it to a foundry, often untrusted, and the foundry will fabricate your design, test it, and then give you back, and you can put it in the supply chain, right? So that's how it works for the ASIC. Then on the other spectrum, you have fully programmable device called FPGA, field programmable gate arrays, and these are devices manufactured by companies like Xilinx, part of AMD right now, Altera, part of Intel, again broken and become an independent company. But anyway, so there are several FPGA vendors like these companies who are developing fully programmable, and these are hardware programmable devices, or the hardware can be programmed or rewired to implement a target application. And this is very attractive in the sense that this is customer programmable, right? So you do not have to go through this complex process of designing your custom integrated circuit. Instead, you take your hardware description and then map it through vendor specific tools to this hardware fabric. Now it gives you huge benefit in the sense that no NRE or non-recurring engineering cost, very high flexibility, extremely short time to market. However, it does suffer from significant loss in performance compared to ASIC, significantly higher power, typically 10x higher power, typically 2 to 5x lower performance, and significantly reduced integration density, because typical FPGA should be about 10 times less dense than an ASIC. So there's definitely a price to pay due to that flexibility and lack of or the fact that there's no NRE. So there is something in between. This is called structured ASIC, and I think you have not heard about that often. This is a paradigm where you have some sorts of programmability. This is called via programmability, where your logic is not logic is fixed, but they can be reconnected in the way you want, and to some extent programmed to implement your functionality by connecting few of the high-level metal vias. Vias are basically vertical connections across metal layers, and it allows you to program that. However, the vias are programmable only by the foundry. It's not programmable by the customer. So if you are a customer, you want to program, you can do that to FPGA, but you cannot do that to a structured ASIC. One of the example of structured ASIC is eASIC. eASIC is a technology offered by Intel. They acquired a company a few years ago to provide that capability. So this is definitely very attractive, very cool technology, and it comes at a low NRE than ASIC, significant cost reduction, significant flexibility compared to ASIC, not as high as FPGA, it's in between, right? However, and of course, it gives you better performance and energy efficiency than FPGA. However, you need to send the design to the foundry for the via programming. So in terms of their life cycle, the way they're manufactured, if you look at that, so that relates to the corresponding trust model. If you think about the ASIC, the designer is trustworthy. That's what you have to consider. But the foundry test and field deployment are not. For FPGA, the only untrusted party would be, the field deployment. During field deployment, somebody can snoop, corrupt things, something like that. For structured ASIC, it follows exactly similar trust model as the ASIC, because you have to send your design to the foundry, and foundry can do anything with your design. They can effectively steal the design. They can do overproduction. They can inject hardware trojan or malicious components in the design. So all the vulnerabilities which you have in the ASIC are also there for ASIC. So I really want you to know that there are three class of technology so that you can understand the corresponding trust and security issues there. Now, why it is important to consider hardware security? Again, I'm trying to make it as informational as I can. So this is a slide I borrowed from SRC, Semiconductor Research Corporation, which basically shows that if you have an impact on the hardware, if the hardware is compromised, then you have billions of devices compromised immediately, right? So if you have thought of, you have probably heard about Spectre and Meltdown attacks, the architectural side channel attacks introduced a few years ago, that impacted billions of processors from Intel and AMD at the same time, right? Because you have exact same configuration in many, many devices. Instead, if you have an impact on the operating system in the form of virus and trojans, then you have probably millions, hundreds of millions of devices impacted. Malwares are much less, maybe 10 to 100,000. And if it's, let's say, a phishing attack like social engineering attacks, then you target few people, right, vulnerable people, and that impact is order of magnitude less than the malware impact. So you see, going from hardware, the impact, the relative impact is order of magnitude less for virus, malware, and social engineering attacks. So the impact is huge. That's number one. Number two is that modern electronic hardware life cycle has a lot of untrusted parties. They are globally distributed. They have a lot of entities involved at different stages, and most of them are untrusted. And if you run the design through untrusted parties for doing many different services, as you can see, from design to fabrication to wafer testing to packaging to assembly to installation of firmware, and finally system integration. So at all these stages, there are potential vulnerabilities on the hardware which can potentially compromise the integrity and confidentiality of the hardware, right? So that's a very, very important point to note. The third important point is that hardware does act a root of trust. So if you are building a system and the system has a complex software stack and system is connected to another device or the net or to the network through a networking protocol, that all of them relies on the root of trust coming from the hardware. It relies on the hardware root of trust, or ROT, right? So there is a chain of trust originating from the hardware, going all the way to the top level software or application to the networking protocol. So because of that dependency, because of that chain of trust, if you have any compromise on the hardware, that will impact the entire system. So that the chain of trust is important for secure software operation. It's important for secure communication, and that's why if that hardware root of trust is broken for any reason or compromised for any reason, then we are in big problem. So you understand hopefully now that the hardware root of trust is so important, and you have to make sure the hardware is secure and trustworthy. This is in this slide we are showing you what to do in a chiplet based 3D IC design to make it secure, and I did refer to that in an earlier slide. So this is a recent work we have done with my postdoc Patanjali. So he came up with the idea of incorporating something called a trusted chiplet, and this is really plug and play. And this trusted chiplet will interface with the other chiplets through the 3D scan standard, okay, as well as the existing 3D IC interconnect standard, chiplet interconnect standard. It's called Chiplet Express, UCIe. So it's taking advantage of the existing test standard and communication standard, such that basically a trust enforcing entity, as you can see at the bottom, can be plugged into a 3D chip, as a secure 3D IC architecture solution so that it can monitor the security and trustworthiness of the other untrusted chiplets. So this whole ecosystem can make sure that in a 3D IC chiplet, we can deal with different security issues and address them in a way that impacts the performance and energy in a very minimal way. It will have much less impact than the extensive encryption-based solution, which I have talked before. That's the current industry standard. But if we follow the architecture which we propose, it can significantly reduce the overhead providing similar security. Another work which we have done recently through a DARPA ACE program as well as Semiconductor Research Foundation, Research Corporation funding is called the security brain Sentry. So it's a security brain that can be connected to a system on chip design. It's very similar to the treehouse idea for 3D IC, but in this case, if you take a 2D system on chip design, and in that design, you can have either a bus-based interconnect or a network on chip-based interconnect. And this system on chip can have different IP blocks, intellectual property blocks. So you came up with another intellectual property block for security enforcement. We call it the security brain of the SoC, implemented by reconfigurable hardware. This is called, the actual name is Sentry. The Sentry is a centralized IP block that can be put into any SoC design as in plug and play IP. And it talks to the other constituent IP blocks like a processor, memory, crypto engine through a security wrapper. You see the green box is a security wrapper, and then after it interfaces with them, it can enforce security for all the other blocks by implementing specific security rules or policies inside the Sentry engine. It's rather simple concept. However, there are a lot of details, and maybe I need 1 more hour to talk about Sentry itself, because this has been a 4-year DARPA project, before that a 3-year SRC project. We have done a lot of work in this domain. What will be the right architecture? What are the security primitives we need to put into Sentry? What kind of security rules or policies you need to put into Sentry? So all those things we have done. If you're interested, we can probably have a separate discussion on that. But by doing that, pretty much every supply chain attack that's possible on hardware we can deal with using this centralized infrastructure. And in this particular slide, I will not go into details about that, but I'm showing you the whole taxonomy of supply chain attacks that can happen on the system on chip, modern system on chips. For example, you can have counterfeiting, we can have hardware Trojan insertion, we can have integrity attacks on the on-chip assets like cryptographic keys or communication keys. So all these supply chain attacks can be dealt with by having this centralized IP called Sentry, which can monitor individual IP blocks and enforce security in those blocks. Okay, so one of the cool thing about Sentry is that it can implement security rules or policies. These are the policies that can safeguard the on-chip assets. System on chips will have a lot of assets like the crypto key, digital rights management key, different configuration bits, different defeature bits, many assets. Firmware, all of these are assets. Even in your personal data, for example, if you have a smartwatch, the SoC or system on chip of your smartwatch will hold your personal data, part of your personal data, and you need to protect those. To protect those, the companies today, if you go to Qualcomm, Intel, Apple, they would implement a lot of security policies. These are the policies that will control access to the assets, called access control policies, information flow, which means how an asset will flow from one point to another point during different operations. Liveness, how long a request to an access would be alive. And then the last one is called talk tower, time of check, time of use, which means that if you have a firmware running in your system, then before you use the firmware, you need to authenticate if the firmware is compromised or not, right? It's called talk tower policies. Now, these policies together will make sure that your SoC will run in a secure fashion. Now, what we did in this particular slide, you can see that Sentry unit is actually implementing all these policies in one place. Traditionally, these policies are implemented in distributed fashion without any systematic design or verification process. In Sentry, we are putting them into one place on a reconfigurable hardware so that you can even patch it in the future. So if you need to change your policy, now we are allowing the users to change the policy or OEM to change the policy after the fact. And this is the first time one came up with a patchable hardware solution. Now, just a summary, just to give you a summary of the hardware security issues in a whole supply chain. This is a diagram which I made a few years ago. So your hardware flows from IP vendor or to the deployment. In between, you have SoC design house and foundry. There are many different threats on the hardware. One can do piracy, cloning. One can put trojans or backdoors. One can do side channel leakage, overproduce, extract design content. So all those things are possible. And so far, people have tried to develop point solutions for those. And there are a lot of different point solutions. So these are the papers, some of the papers we have written from our lab. And there is no integrated design flow that can deal with an unified security or trust sign-up process. So that something has not been done. We have started working on that topic. So these are some of the tools which we have developed to deal with security issues as a point solution, which means that each of the tool can deal with one specific threat. Okay, this is the entire life cycle for a system on chip design today. And as you can see here, there is a need for combining these tools, which can address all the security issues in a holistic manner as opposed to fragmented point solutions. And one interesting thing to note here is that AI has a big role to play in terms of generating attack vectors. It can predict new attack vectors from the known attack vectors. AI is good at that. Particularly generative AI is very good at predicting attack vectors. AI is very good at predict with verification. And then, of course, Gen AI, or different forms of LLM is being used for security verification. And AI is also good at design space exploration for security. So we'll not have time to talk about that, but AI can play significant role in secure design. So I do not have too much time, but I will talk about a couple of really important challenges in hardware. One is the confidentiality of the hardware itself. How do you protect the hardware as an asset? So if you want to make sure that the untrusted parties in a foundry or even after it's fabricated cannot clone the design, cannot reverse engineer the design or clone the design or cannot exfiltrate the design secret, then you have to transform the design or you have to remove information from the design. Now, one way to remove information is that you take the critical part of the design and replace it with a reconfigurable block. In this case, we'll have tried to replace it with eFPGA or embedded FPGA block. This is a very important new direction of for protecting hardware against different confidentiality attacks. And in this case, what people are doing is that they are developing a tool to isolate the critical part and replacing it with the reconfigurable part. Now that comes with a very high overhead. In our calculation, the overhead can be easily 20 to 100x. We have been working with Intel Corporation through a funding from OSD, and our partners in this case are University of Maryland and Intel researchers. We also have worked with the National Security Agency, and we have come up with a tool called Reaper. Reaper is basically a tool which can, given a design, can take the design and then provide fine-grained replacement of critical logic using reconfigurable logic. So that's the Reaper, and by doing that, if you can look at this, the table on the top right, you can have significantly better area compared to eFPGA-based solutions. You can have significantly better delay power, the bit stream size would be much less, and also you can have better security. So that's about protecting confidentiality of the hardware. We have also done a lot of work on protecting integrity of the hardware, where you want to make sure that the hardware is not tampered in any way. And there are many ways to tamper, but these are the high-level models of tampering of a hardware. You can have a combinational modification. It's called combinational Trojan, where you have one node of a circuit modified, one or more nodes modified based on the condition of the other nodes. Okay. It can also be a sequential Trojan where you modify some internal events or internal nodes by having a sequential machine, like in this case, a k-bit counter. When the counter counts to a specific value, you change the internal node. Okay, so this is a very, very difficult problem to detect. So if somebody modifies your hardware and you get back the design or the fabricated chip, how do you verify that nothing wrong has been incorporated into a billion transistor design? Right, it's very, very difficult problem because one can just alter few transistors here and there, and then it can change the functionality quite a bit under a very rare condition, which you will not be able to detect. So the fundamental difference between traditional verification and trust verification is that we are not detecting bugs which are unintentional, we're detecting intentional malicious changes, and it's not typically bounded by spec, which basically means that it's a much bigger verification challenge. The search space is way bigger than that. So to be able to detect a malicious modification, we need to use machine learning. I believe machine learning can play a huge role in detecting malicious modification, and we are working on that. This is one solution we have developed. First, you have to create a lot of possible Trojan attacks in a design. To do that, we use generative AI so that it can figure out how the Trojan is incorporated into a design and then eventually incorporate those Trojans into your design. So that is very important because if you have a machine learning tool to detect a malicious instance, then you need to have a large data set to train, and this can do that. And these are the potential use cases for that. But the most important thing is that we came up with a machine learning tool to detect Trojan in a design when there is no golden or reference design. Okay. And this is called Viper. This is right now funded by CSME at Purdue University, and that funding comes from TSMC and Synopsys. The whole idea here is that you have a simple classifier, machine learning based classifier, typical supervised classifier you have in machine learning, and this classifier will be trained to detect a malicious instance or tampering or Trojan. How do you do that? We basically look at the property of Trojans in terms of its functional behavior, in terms of its structural properties, in terms of its neighborhood properties or the connectivities to other nodes. We looked at 30 different properties in total, and then we trained the machine learning based classifier to detect a Trojan instance based on those properties. And once the training is done, then you can put the new design into that, and then this will basically be able to detect an unknown Trojan in your design. Of course, there will be false positives. You can do post processing to reduce the false positive, but it gave us huge accuracy of about 99.69% to 99.88% if you can develop such a machine learning model. And one can, looking at these 30 properties, one can also try to figure out which properties are more important through information gain analysis in machine learning. And we did that. And we came up with a very powerful tool that can detect Trojan for a given design. So with that, I will quickly go to one specific contribution, which I will talk, and then I'll finish my presentation today. This particular one is using generative AI, particularly LLM, different LLMs from Gemini and ChatGPT, different versions of ChatGPT. What it's trying to do is to come up with an end-to-end secure design flow. So can you use the LLM to develop an end-to-end secure design flow? This is a hot topic right now. I know a lot of research groups are doing work in this area because LLM is so powerful that people are trying to use LLM in many different areas of security design and security verification. So in this case, what we are doing, you're taking a system on chip design, and then we're asking the LLM to generate the relevant security bugs, security issues for that system on chip design. How we are doing that? We are actually generating a set of context information which we call SOC configuration, and that's something we are doing by using our tool. We have developed a tool which will do submit a set of queries to the SOC, and then the SOC will provide the information. Those informations are giving to LLM. LLM will have enough context to figure out what are the relevant CWEs. This is a database which is prepared by MITRE Corporation. The public database would list all the possible known hardware vulnerabilities called common weakness enumerations. And these vulnerabilities are there in a database. LLM would be able to figure out for this context which CWEs are relevant. And then finally, for those CWEs, we'll create SVAs or system value like assertions. So these are the checks, like in C, you can have assertions. These are the checks which will make sure that security issue is not there in the design. And finally, you will create the corresponding policy by using another tool called Dispel to implement the policy checks inside our Sentry engine. So this is the whole ecosystem we have developed using LLM. LLM is used at 2 stages, as you can see here. This is the entire flow. And if you do that, it does a fantastic job in completely automating the whole process. It will find the security flaws which are relevant for your design. You'll implement a check. Finally, you will go. That check will go into hardware. So this is very, very powerful, very promising. It has some problems. For example, it doesn't have enough contextual information, so we have to work really hard to give it the right context. And sometimes when it finds a security flaw, it doesn't have enough logical reasoning. So that's something we have to deal with. But we are ways to address them. We are actually working to improve the whole framework, which is called SPEL, to be able to provide more domain-specific information and then do post-processing to make the final security solutions as good as we can. So in summary, we need to have a full-fledged security trust sign-up process coming from the IP to the actual tape-out, actual hardware. So that is not there today. It requires effective integration of the existing solutions, and maybe it requires new solutions. But if you can do that, that can be truly enabling, and that's the need of the hour, I believe. And finally, AI has a big role to play in many ways, not in all possible scenarios, but in some important aspects, AI can play increasingly powerful roles, and that needs to be explored. So with that, I'll stop, and I'll be happy to take any question.
Thank you, thank you so much, Professor Bhunia. I really appreciate it. It was amazing. There's a lot of interesting ideas, and well in line with what you're trying to convey out of this colloquium, which is we really have a national security obligation to pay attention to the assured microelectronics, and initiatives you shared and ideas you contributed are well in line with that. I really appreciate that. We have like maybe room for 1 or 2 questions. I can ask them like based on what I got. One of them is, how close do you think we are to the cyber trust mark, basically aspect? Like we know, we keep talking about this having, when I want to buy this device, I want to make sure it was vetted, it's a good one, it's verified, its design was verified, and it's ready for me to use it without a lot of concern. How do you think are we close to that? No.
No, not at all. That's a very, very important research topic that given a system, particularly if it's a commercial system, how do you verify the trust? Maybe let me pose the question in a different way. If I am the end user, and if I, let's say, buy a device from a supply chain, maybe from Amazon or DZK or whoever, right? How do I verify the trustworthiness? How do I verify the security for that device? There is no tool out there which will allow an end user to do that. Even for the system integrator or the OEMs, there is no tool out there. And when I said that there has to be end-to-end flow for security sign off, so that is another one which one can do at system level. For chip level, yes, we are working on that. We have made good progress in coming up with an end-to-end security design, security verification process. But for system level, there is nothing there also, and there is a need to come up with such a tool. And of course, for students and professors, that's a very, very important, very interesting research area.
Okay, thank you. I have one more question that's there. It's, like design is always mainly about the future, making sure that we improve our future, make our system more secure. How about the design for the past? It might be interesting question, but the issue is,
Yes.
the penetration of microelectronics is huge. It's even every aspect of our life. We see it in all these air conditions, on all these fridges, and all, which is we cannot replace overnight.
Yeah.
Now, how can we deal with this design for the past?
Yeah. So first of all, I'm doing some interesting work on securing the binary, not the hardware, but the software for which there is no source code. So there are many binaries for which there is no source code. So this is a new collaboration I have started with an institute in India called IIT Madras. And then what we are trying to do, we are taking a binary and doing some fudge testing on the binary to find out security flaws for the binary and then potentially patch it. For hardware, the only way to patch it today is to change the firmware. So if you can find a bug, security bug for a hardware for existing system, if it is fixable by changing the firmware, there is a chance that we'll be able to change the firmware and fix the bug. If the bug is in hardware, there is no way to fix that. So we have to potentially discard that system. So yeah, unfortunately for existing systems, there is very little technology to verify the security issues. There is very little technology to fix the security issues. A pretty open domain for research.
Okay. Thank you so much. It's 2 p.m. here, Chicago time. Really appreciate your time taking your busy schedule, sharing all these amazing research ideas and your extension of interest to support other universities is amazing to us, and we're really thankful to that. And this concludes this part of the presentation. And if you have any comment, a final comment, Dr. Bhunia, you're welcome to say it.
Thank you very much. First of all, really appreciate the opportunity here, and I will be happy to answer any questions. If you want to send me via email, any communications, I'll be happy to respond to that. And of course, I look forward to the opportunity to work together in future.
Thank you so much, Mr. Bhunia. I really appreciate your time. And this is like 2 p.m. Chicago time, which is like we're concluding the colloquium on behalf of Chicago State University and on behalf of IB-Tech, and also on behalf of an IC2Tech project. We'd like to thank all attendees and students, faculty, and researchers for taking the time to be here all these 4 hours and to ask the questions. And anybody who helped us get this colloquium together, we really appreciate them also. This is into the colloquium, and we'll. I know this colloquium we did not cover all the issues related to assured microelectronics. Is a huge topic that needs a collaboration of many researchers from different institutions, government, public, universities, private institutions. We have all to work together to deal with this critical problem because it's impacting all of our aspects of our lives. Again, thank you, and we'll see you again in the next activity.